Welcome to homework.
All right, so problem number 19 states that an electron is in a box of width 3 times 10 to the minus 10 meters. What are the de Broglie wavelength and magnitude of the momentum of the electron if it is in A, the n equals 1 level, B, the n equals 2 level, and C, the n equals 3 level? In each case, how does the wavelength compare to the width of the box? So, starting with the de Broglie wavelength for an electron is given by lambda is equal to h over p. And relating that to the energy of the electron, it's equal to h over the square root of 2me, because the kinetic energy is equal to p squared over 2m. All right, so now also from equation in the text, we're given the energy of each quantum level of the particle in the box. E sub n is equal to n squared h squared over 8 ml squared. So now we can plug this in for that, for this E in the de Broglie wavelength, and we get lambda is equal to h over the square root of 2m times n squared h squared over 8 ml squared. Now some simplification, those cancel, and then these become 4. So we're left with 1 over the square root of n squared over 4l squared, which is equal to the square root of 4l squared over n squared, which is equal to 2l over n. So here's how the de Broglie wavelength is going to relate to the box length and each subsequent energy level. So it's basically lambda over 2 is equal to integer values of lambda, which is the box length. So for part A, it asks for n equals 1. I'll put for part A. So lambda 1 is going to be equal to 2L over n, which is equal to 2L, which is equal to 2 times 3.0 times 10 to the minus 10 meters, which is equal to 6.0 times 10 to the minus 10 meters. Now for the momentum, if we have lambda is equal to h over p, then p is equal to h over lambda. So the h over lambda, which is equal to 6.626 times 10 to the minus 34 joule seconds over 6.0 times 10 to the minus 10 meters. Which is going to be equal to all right, 1.1 times 10 to the minus 24 kilogram meters per second. All right, so that's for part A. For part B, n equals 2, so lambda is equal to 2L over 2, which is equal to L, which is equal to 3.0 times 10 to the minus 10 meters. And the momentum is equal to h over lambda, which is equal to 6.626 times 10 to the minus 10 meters. Sorry, that's not meters. I got distracted. There we go. Joule seconds divided by 3.0 times 10 to the minus 10 meters, which is going to be equal to 2.2 times 10 to the minus 24 kilogram meters per second. So for part C, n equals 3. So lambda is equal to 2L over 3, which is equal to 2/3 times 3.0 times 10 to the minus 10 meters, which is equal to 2.0 times 10 to the minus 10 meters. And the momentum, P, is equal to h over lambda, which is equal to 6.626 times 10 to the minus 34 joule seconds, divided by 2.0 times 10 to the minus 10 meters, which is going to be equal to 3.3 times 10 to the minus 24 kilogram meters per second. Now, if you note, for 1, it was 1.1. For 2, it's 2.2, and for 3, it's for 3.3. So we can say P3 is equal to 3P1, and P2 is equal to 2P1. Now, finally, for the last part where it asks about how, in each case, how does the wavelength compare to the width of the box? I mentioned this at the beginning, but I just want to kind of go more formally into it. So lambda n is equal to n is equal to 2L over n. So the length of the box, L, is equal to n lambda n over 2. So it's integer numbers of lambda over 2 is the relation to the wavelength and the width of the box.